All right, 6-1, new topic, last topic, key features of exponential graphs. And exponential is in the news quite a bit this past year because things would rise exponentially. So we're going to talk about and learn what that is. For our first example, it says to graph. So first thing I did was go to Desmos and copy a graph. So I just made a little image here, what it would look like. This is what it looks like. So when we're talking about the domain, it gets wider and wider and wider. So it goes to the right forever. And as it's going up, it goes left. So we say that it's negative infinity to infinity. Okay. So if you forgot what domain is, that's left to right. So range is bottom to top. So the very bottom of this graph mellows out at what we call an asymptote, okay? And what it means is it's getting really, really close to this y-axis, but it's never actually touching it, okay? So the range is from 0, and then it goes up, up, up forever, so we say infinity. It does not touch at 0, so we close it with a parenthesis, not a bracket. The asymptote is the x-axis, and if we want to write the equation for the x-axis, that's y equals 0. So either one of those answers are acceptable. And so in behavior, we've talked about it before, it typically confuses us, that's okay. We have to talk about two ways. So as x goes to negative infinity, what that means is as x is going left, what is the graph doing? Well, it's going up. So to say up in math terms, we say y is going to positive infinity. Now, as x is going right, remember it's mellowing out at almost 0, so we say that y is approaching 0. Transformations, again, we have hit them in every topic except probability because we didn't graph in probability. We're going to hit them again. So remember, if the plus is with the x, it means to go left. And it's going to go left however many that number is. So in this case, left 3. If I had a number on the outside, so for instance, that minus 2 would be down 2 because it's on the outside of the function. It's not grouped with x. Okay? A negative with the x means reflect over y-axis. If you had the negative out front, it means to reflect over the x-axis. All the same rules that I feel like we've been tested on over and over and over again still apply, just it looks a little different to be exponential because exponential, in case I didn't say it from the beginning, is when the x is in the exponent, hence exponential. Okay, so real world problem, I know it seems scary, but it's not too bad, especially when they give us the function like this. It says a factory purchased a 3D printer in 2010. The value of the printer is modeled by this function where x is the number of years since 2010. I feel like that's the hardest part right here. We want to know what is, and it's not in this type of problem. It's only hard whenever they're like, what about in 2020? You have to know that that's 10 years later. That makes it hard. Backing up, we're going to graph this, And then we're going to find out when x, or after 10 years, so x is 10, we're going to figure out what y is. Okay. So I typed it in. I can't even see it. There we go. It's there. I could I could trace it. You know how you can trace all the points until I got to 10. Okay. So there's my answer. Or your other option is to hit settings and hit table and type 10 here. So 14 and a half. So 14, I didn't look at that as money, so 14 and 52 cents. Okay. Does the printer lose more of its value in the first 10 years or the second 10 years? So let's go back and look at our function. And I'm going to put 20 down here because another 10 years would be 20. So I think about the difference from 30 to 14.52. Okay, that's 15.48. So the difference for those is 15.48. But from 10 to 20 is only 7. 7.5. So answer here is the first 10 years. And part of the reason that that is true is because anytime your b value, so the value that you are raising to x, is smaller than 1, it is called exponential decay, because as you saw in the graph, decay means that, whoops, let's go back to the marker. Decay means that it's going down, down, down. So things like your car value would be a decay. An exponential growth model goes up, up, up. So examples of growth would be population, bacteria growth, virus growth. Things like that would be exponential growth versus decay. If you write nothing else down, I suggest that you write this under growth and this under decay. Okay. We find growth by saying 1 plus the rate, but we find decay by saying 1 minus the rate, whatever that rate is. Okay. So if I look at this interpretation, we're given the function here. Oops, I thought I was still on highlighter. And it's modeling the number of hawks in a region after 2016. We want to know, is it increasing or decreasing? So what we do is look at the value being raised to x. Is it greater than 1 or less than 1? Well, that's greater than 1, so it must be increasing. Also, if I graphed that function, I would notice that it's doing this, which would tell me that it is increasing. Okay, in what year will the number of hawks reach 280? So I'm going to clear out what's here. I'm going to type in that function it gave me. So it was 220 times 1.05 raised to the x. And I want to know what it would be, when does it reach 280? So I could say y equals 280. Find that line. Find out where they intersect. They intersect at 4.9, which let's round that to 5. Okay. Or let's see, actually, sometime before the 5th year it will reach 280, right? So before the 5th year. If we go back and look at our problem, 2016 is when we started. 5 years from that is 2021. By then, it will have surpassed. Once it hit 5 years, it would be over. It would hit sometime in the 4th year. So 2016 plus 4 is in 2020. All right, so that is an overview of 6-1. Try your practice and your